Hi, welcome to the Signal Path. In this episode, I have 3 reviews of 3 items that I've received in the mailbox, which I think are all very interesting. So I'm eager to show you what they're all about. But before that, I just wanted to give you a couple of updates as well. A few videos ago, I mentioned that I would give away the Patreon proceedings for that particular video. Well, we've done it. I went to a website called One Simple Wish, which is focused on granting wishes for mostly children in foster care. So we went ahead and we granted about 20 wishes or so from different children from all around the country. And I have to say, it's both a rewarding and a heartbreaking experience because of you see how little it takes to give somebody something they really need. So please, if you can help, go to that website on oneSimpleWish.org and give, or any other charity of your choice. And thank you to my Patreon supporters. You guys are incredible. Not only are you helping the lab, but occasionally I'll be able to donate this in your names because of all the contribution you're making. And the other thing is that I promise I'm going to do more giveaway to everybody, including my Patreon supporters. Well, today we're going to start with this Keysight DSO-X 1102G, which is a 2-channel oscilloscope, 100 megahertz, 2 gigasample per second with a built-in function generator. This is a great thing to have on your bench. And I wanted everybody to be eligible. So in order to give an advantage to my Patreon supporters, this is what we're going to do. So everybody who wants this, and please only put a comment about wanting the item if you really need it. So allow other people who actually can't afford it to have a chance. So leave a comment that you want it, but make sure you are a subscriber, because I'm going to take all my subscribers and I'm going to look at all the comments and then I'm going to draw from that. At the same time, if you're a Patreon supporter, you're automatically involved, you're automatically included, which means that if you leave a comment and you're a Patreon supporter, you actually increase your chances. And to help you guys, I'm going to draw 1 from the comments and 1 from the Patreon supporters, and between those 2, I'm going to draw again. And that's going to give more chance to the people who are Patreon supporters, just so that I can support them in some way because of what they're doing to the website. So this is just the first of the many giveaways. It's going to be in the future, and it's going to be different kinds of instruments and even better instruments than this one, although this is a pretty awesome thing to have on your bench. So I'm eager to get started with the reviews. Don't forget to do the thing I said, subscribe, leave a comment, and if you're a Patreon supporter, you are there, leave a comment also to increase your chances. Let's get started. So our first item of interest are these fast rise and fall time edge generators. These are really interesting units, and we'll take a detailed look at them. And these are from Leo Bodnar Electronics Store, and definitely take a look at them. I put the link in the description so you can easily find the store and see all the other interesting things they have on their store. They also sent me a coaster and a box of cookies, which unfortunately is empty because somebody ate all the cookies. But they also sent me 2 versions of their edge generators. One of them is using a BNC connector at the output, and the other one is using a 2.92 millimeter connector to get even faster rise and fall time, of course, because the frequency response of the 2.92 millimeter connector is far superior than the SMA. We're really pushing the SMA properties here, and they have used some interesting design techniques for that. It also comes with an SMA male-to-male converter, so you can connect your 2.92 millimeter connector to the instrument that you want, but I'm going to use a 2.92 millimeter converter as well. These are pretty expensive, so this version actually is almost twice as expensive as this one because of the difficulty in creating that connector and making and purchasing the connector itself. Now I'm a little bit surprised that they're using a female connector here. I would have certainly used a male connector because most of the time test instruments have a female connector themselves, which would make this to be able to be connected directly to an instrument without a conversion in the middle, because you don't want any conversion, but perhaps they couldn't source one, or for whatever reason they thought the female version would work better. But either way, we're going to be able to connect this to a whole lot of different equipment around the lab. But first we need to understand exactly how they work and take a close look at them. And here we have the 2 units side by side, the SMA and the 2.92 millimeter version. Now from an electrical point of view, they're essentially identical. They're using the same components, same interfaces, same functionality, but of course the transition to a much better connector is first of all a little bit more difficult, and also preserves the signal integrity and the bandwidth of the interface, which is why the 2.92 millimeter one is going to have better performance. So let's take a look at the one on the left. This is a BNC version. In the center we have an 18F microchip microcontroller, a series, and this allows you to use the 3-wire interface to configure the output driver IC, which we will talk about in details and look at this block diagram and exactly how it works. So this IC not only communicates with the output driver, but also communicates with the USB, allowing you to use a GUI to configure some of the parameters of the output driver, and I'll show you that GUI too. Aside from that, I don't think this microprocessor really does anything else. On the top left, we have a 10 megahertz crystal. Now this is the source of the 10 megahertz square wave that goes to the output, and it goes through a little amplifier and splits into 2, and one of it directly goes from here AC coupled into our output driver, and the other one goes into the trigger output. It's nice that they have provided a trigger output because if you're using a subsampling oscilloscope, you need a trigger in order to be able to synchronize the scope to the edge measurement you were trying to make. And of course, this makes it more usable as well if you wanted to jitter decorrelated measurements on a regular oscilloscope, so that you can trigger on this and measure on that and create an eye diagram and all of those good things. So I'm glad to see that the trigger is included. USB connector, pretty straightforward. If you don't want to use the GUI interface, all you need to do is to just provide power to it, so it doesn't really need a computer interface, as we shall see. Now, if you look at the output driver here, this is a differential in, differential out, but we're using it in single-ended mode. You can see one input terminated there, one input terminated there, both into capacitors, so they're AC grounded, and an AC coupled directly to the center pin of the BNC. Nice little circular holes that you can see all around the center pin, removing as much dielectric as possible to emulate an air transition dielectric as closely as possible and to reduce dielectric losses. It's a nice little interface transition, which I'm sure they have optimized using EM simulation. All the view stitching, all the ground path is nicely done there. Now, of course, you don't need to do all of this when you have a 2.92 millimeter connector, because the transition is designed with the tolerances and the distances to already provide a very good interface. Now, you don't have room here to remove the dielectric. Perhaps they didn't want to go through all that trouble. It's really not necessary, but you can get a very good transition there as well. Similar interface, you can see a smaller capacitor, 2 in parallel directly to the output, allowing you to get even better rise and fall time. Same trigger, same crystal, same microprocessor. Everything else really is the same. The magic is all in the transition. Now, we do work up to 100 gigahertz with such transitions, but getting a broadband transition to work very well is quite difficult rather than doing a narrowband one. So having a good impedance transition across a wide frequency ranges can be challenging. On the other side, really nothing else going on. Just the brand name, the revision J, I think this is, the website and everything else is listed. Other than that, it looks really nice. I like the transition they've done on the BNC to optimize the performance as much as they can. So we're going to now take a detailed look at the block diagram of this IC and learn exactly how it works. And once we're satisfied with that, we can go around the lab and connect this to many different scopes and see what we get from the instruments and see what kind of performance we expect to see from the different brands of equipment I have here in the lab. And here we have the functional diagram for the MAX 3949 IC. Now, this is the IC that directly drives the output of these edge generator blocks, and you're dealing with basically these two outputs. So how does this thing work anyway? Well, this is nothing more than an AC coupled laser driver IC, and its intended purpose is for optical communication, but it is rated up to 11.3 gigabit per second. That means that in order for it to produce a perfectly open eye diagram at 11.3 gigabit per second, it has to have very fast intrinsic rise and fall time. In this case, it's rated about 25 picosecond of the IC with the QFN package altogether. So that means you should be able to produce very nice eye diagrams at 11.3 gigabit per second even after the laser diode modulation, and that's exactly what this does. Now, the intended purpose is for datacom, but we're using it for its fast edge properties and just generating a square wave at its output, getting the highest rise and fall time we can get from this block. Now, the input is intended to be used from a backplane directly being driven into the IC, so it has its own internal 50 ohm termination. Of course, that's all normal. This is how all of these ICs are supposed to be made. And then we have an equalization block, and this equalization gives you preemphasis before the signal is transmitted out of this IC. And in fact, the equalization is set to operate at 5.6 gigahertz, and you can get a couple of dB of equalization preemphasis peaking essentially directly built into the chip. Now, if some of this sounds foreign to you, I did make an episode a while ago on the idea of data transmission and signal equalization, where I go over all of these concepts and I actually show live demos of how an eye diagram is affected by various types of equalization. So make sure you check that. Some of this material is definitely covered there. Now, because this is a laser diode modulator, if the input signal is lost, so if the data coming in disappears, you want to make sure you disconnect the output and you stop the modulation of the laser. That's why there is a TX loss of signal detector, which then goes over here and then can control the output directly. And then you can even read that from a host processor that something bad has happened. You can reverse the polarity of the signal going out, so if you need to invert or not invert, that's transmit polarity control is easy. And at the output, you have a differential pair open collector for high output current drive capability. And then the terminations 25 ohm are actually also on chip. And this is then goes out and intended to be AC coupled to a laser. So it's very straightforward. Everything else is transmit mode setting, output amplitude control, and all of the other things are of course all digitally enabled through an SPI interface of some kind, I2C3 wire interface, so whatever they're using in this case. So really pretty straightforward, nothing unusual there. And we're using this as with a square wave input. So even the square wave input is not going to have very fast rise and fall time. By the time it goes through this chip, because it is an NRZ, non-return to zero type generator, you get rise time multiplication. So you get very fast rise time reduction because of how fast these circuits are internally, and there is gain in the transmit path. So you're able to get very good rise and fall time. So you don't have to put in very fast rise and fall time to get very fast time, as long as you run it in a nonlinear mode. So the chip is pretty straightforward. And one of the other nice things about this is that they have written a little tiny USB fast pulse generator interface GUI, which you can connect. Once you connect it to the USB port, you can then change the output amplitude, and the calibration coefficients can be adjusted. It's a nice little block, but you don't need to open it. You can just directly plug it into power, and then you get all the features, or you just get the square wave coming out of it. So it's all set to be used. Now that we know exactly how it works and we have an idea of its construction, we should be able to go ahead and connect it to some instruments. I have so many scopes here in the lab, and I'm very curious to see how each of the scopes behaves. Let's go hook it up to a lot of equipment. So let's go ahead and measure some instruments. Now before we do that, we have to establish a few things. First of all, I'm going to use the BNC version of the pulse generator for every instrument that has a standard BNC input. Once the input changes to high performance BNC compatible inputs, then I'm going to use the 2.92mm version with the proper conversion kit, and I will show you that once we get there. So for everything else, let's go ahead with this one. Now, in order to estimate the 3 dB bandwidth of the instrument, you still need a couple of other information, because you need to know what kind of front-end filtering is internally implemented inside the instrument. Is it maximally flat? Is it Gaussian response? Is it what kind of interpolation they're using? But in all cases, a number of roughly around 0.4, 0.5, 0.45 divided by the rise time, which is defined as 10 to 90%, is a good approximation of the bandwidth. So in this case, we have a rise time from the Regal DS6104, which is a 4-channel scope, 1 GHz bandwidth, 5 gigasample per second. We're getting something in the order of 340 picoseconds on average. Now, using 0.425 as a ratio for roughly estimating the bandwidth, we get a bandwidth of about 1.25 gigahertz, which is more than the bandwidth that is written on the front of the instrument. And in fact, if I remember correctly, when I was testing this, this does have a little bit more bandwidth than 1 gigahertz. So it has a fairly good front end from that point of view. So here's our first test. For the Regal 1 gigahertz, we're getting 340 picosecond for the rise time. Let's go to another scope. So how about the LaCroix HDO 6104? This is a 12-bit scope, 1 gigahertz bandwidth, 2.5 gigasample per second, 4 channels. And LaCroix excels in their data processing that you can do when the data after is captured. They have a really rich set of functions that you can apply to your waveforms. So in this particular case, we're getting a rise time of about 430 picosecond, which if I use a multiplication of 0.425, I get about 990 megahertz of bandwidth, which makes sense. This is a 1 gigahertz instrument, and you can see the individual dots. This is a sin x over x interpolation. The individual sample points at 2.5 gigasample per second. It looks good, seems to meet its spec, and we're getting the numbers we're expecting to get. And here is the Tektronix MDO4104C, which is also a 1 gigahertz instrument, 5 gigasample per second on 4 channels. This is a mixed domain instrument. I did a full review and teardown of this. This is definitely one of the most versatile oscilloscope, mixed domain oscilloscopes you can currently get because of the full spectrum and time domain and digital domain correlation methods that it has built into it. So now on this one, on channel 1, we're seeing a rise time of around 330, 340 picosecond also, which is about the same as the Regal. Certainly meets its 1 gigahertz bandwidth requirements, perhaps a little bit even more than that. And it looks really good. This is what you would expect to get from Tech as well, meeting their 1 gigahertz requirements. Let's keep going. Of course, you're not limited to using instruments that have a 50 ohm termination. You can use something like the Rodenschau's RTB 2004, which I've also reviewed extensively. And this particular one has only a 1 mega ohm input, 300 megahertz bandwidth. Now, when you run this with a 1 mega ohm input, the swing output of course is going to change because it doesn't have the proper termination anymore, but that doesn't really matter so much because we're not pushing this to its limits anyway for an instrument that doesn't have 50 ohm input, so you're still measuring the limitation of the scope even in that condition. So here we are seeing a rise and fall time of about 1.5 nanosecond, which is consistent with the 300 megahertz bandwidth of the RTB 2004. So which means that you're still pretty good using this in 1 mega ohm input, as long as you're not of course pushing it, but there's not going to be no scope with a 1 mega input condition that has sufficient bandwidth to really push this unit to the edge of its performance. So that looks good also. Let's keep going. And here, of course, we have the Tektronix 5 series, the 8-channel oscilloscope. It certainly became one of my favorite oscilloscopes here in the lab. That's why it's sitting on the repair bench because of its versatility, quick responsiveness, and there's so many channels you have here to play around with. Now, in this one, we're still using traditional BNC connectors. Because of that, I'm still using the BNC version of the Edge generator there. This is a 2 gigahertz oscilloscope front-end bandwidth, and that's why we're getting a rise time of around, less than 210 picoseconds, which corresponds to about 2 gigahertz of bandwidth. And look how nicely it averages the waveform. It does a very good job at capturing and averaging, and of course measuring the rise time. And here you can even plot the statistics of this and so on, but it's roughly about 205 to 210 picosecond. So this looks good. You can also measure this on all the channels, looking for differences between the channels, but they're calibrated, so they all have their frequency response compensated to give you roughly the same result. So it looks pretty good. Let's keep going. So now as we move to higher bandwidth oscilloscopes, we're going to have to change our connector. BNC is not going to hold it anymore. So here I have a special transition that transitions from a BNC compatible connector to a 2.92 millimeter connector, and then I have a 2.92 millimeter converter to connect directly to this edge generator itself. Now this connector, it costs a fortune, but if you buy a scope that has high enough bandwidth, they will certainly give you a number of these depending on how many channels you have. So I have a couple of these because of the S series oscilloscope from Keysight, which we'll get to in just a second. Now I did make a quick error there. This is actually not AC coupled. This is DC coupled with a 25 ohm series resistor at the output, as the datasheet requires. So unlike the BNC version one, this is DC coupled, and this is going to give you a little bit better bandwidth because of the fact that you don't have any parasitics associated with AC coupling something. So when we do this, we have to apply a 0.5 volt offset to the scopes to center the waveform, but I made a mistake. I thought those were capacitors. They are not. So here we have the Keysight MSOX 6004A. This is a 4-channel 20 gigasample per second scope with about 6 gigahertz of bandwidth, and it has 2 built-in generators. It has voice control, so you can talk to it and tell it to trigger and capture and stop. It's very useful when your hands are busy working on a circuit. It's a really great instrument. So having said that, it's measuring a fall time of about 65 picosecond. Now 65 picosecond is excellent because if I use a 0.425 multiplication factor, I'm going to get a bandwidth of about 6.5 gigahertz, which I think in fact I've measured, and it does indeed have more than 6 gigahertz of bandwidth, but at least the very minimum it does meet its 6 gigahertz bandwidth requirement. And the fall time is a little bit faster on these units, on the edge generators, than on the rise time. So I'm going to measure the fall time from now on all the other instruments. But as you can see, we can get down to 65 picosecond with the MSOX 6004A. So how about the Rodenschwarz RTO 2064? This is also a 6 gigahertz, 20 gigasample per second instrument. Excellent noise and performance on this unit as well. Now here I'm measuring the fall time, and I'm measuring it about 75 picoseconds, which is about maybe 10 to 8 picoseconds slower than what I'm getting on the Keysight, which is a little bit surprising. Perhaps has to do with the input filtering of this. It still meets the 6 gigahertz bandwidth. It's just that the Keysight one exceeds the 6 gigahertz bandwidth, so the rise and fall times are going to be a little bit different, but nonetheless this also has the high performance BNC connectors in the front, so I'm using the same connector for it. But as you can see, we also have an excellent performance coming from the Rodenschwarz RTO 2064. And how about the Keysight MSOS 804A, 8 gigahertz, 20 gigasample per second. Again, I've done a full extensive review of this instrument showing tons of different capabilities. This is one of the lowest noise, highest dynamic range instruments on the market. And so we can see with this one, we're getting under 52 picosecond on average for fall time, which is to be expected. This instrument has more than 8 gigahertz of bandwidth, 8.4 gigahertz in fact of bandwidth, and we're getting even less than we were getting with the other Keysight instrument. So now I have one more instrument that has even more bandwidth. It's actually an older unit, but we want to see if I can push this to its limit. But the Keysight MSOS series, meets the specification as just like you would expect it. And in my test I've done and I've shown the ENOP measurements of this instrument, done constellation, eye diagrams, everything you can imagine. This is a really great oscilloscope. And here we are with the Agilent DSO 81304A. This is a 13 gigahertz 40 gigasample per second instrument on 4 channels. It's actually quite old. It doesn't even have a USB port in the front, so I have to power the module with an external battery. But nonetheless, this is the highest bandwidth we have at 40 gigasample per second. And if you take a look, we have a rise time of just under 40 picoseconds, 39.1 picosecond. But if you go to the fall time, as I was saying, the fall time is indeed a little bit faster. We're getting under 34 picosecond. So 34 picosecond is now at the edge of the capabilities of this unit itself. So I'm not quite convinced that we're measuring this instrument. We might be measuring all the transitions and everything else that's connected to the edge generator itself to get less than 34 picoseconds. I know it's spec'd about 30, but that's probably at the edge of that connector. I'm not quite sure, but nonetheless, you can see that we're getting very close to the 13 gigahertz bandwidth of this oscilloscope, and we're getting the rise time we expect from a 13 gigahertz instrument. So that kind of covers all these scopes pretty much I have in the lab, or at least all the interesting ones. So I hope that you enjoyed this review of these units. I think they're very interesting and very cool to have in your lab. Certainly the higher cost version is only useful if you can take advantage of the 2.92 millimeter connector, and I wish you had a male connector, but everything looks really good. So let's go to our next item. And our next item is this GPS discipline oscillator. Now, as you know, GPS discipline oscillators are extremely useful to get very accurate frequency reference so that you can lock multiple things together, or if you're looking for an extremely accurate reference that's locked to the GPS. Now, this is a pretty flexible one because not only does it lock to a GPS, it also is fully programmable to generate 2 independent outputs anywhere from essentially DC to about a gigahertz. So right now it's by default configured to produce 10 megahertz and 200 megahertz differentially, but you can configure it in any way you want. I'll talk about that once we look at the schematic and the design of it. There's also a bandpass filter here so that you can use it at exactly 10 megahertz, so you get a nice sinusoid out of this as opposed to getting the square wave out of the unit. So it's really quite nice and flexible. This is from the guys at SV1AFN. I don't know if there's a particular way to pronounce that, but this is SV1AFN.com. I'll put all the links and everything you need in the video description. These are the same guys who made these really awesome rulers. These are microwave rulers. You can see all different kinds of components labeled in the back, and I have another version as well, which is longer with a lot of really cool stuff on it. This is probably my favorite art rulers, PCB ruler kind of things that I have here in the lab. This is the same guys who are designing this. They also have tons of other projects on their website. Definitely go check them out. I'll put a link there so we can look at it, but let's take them apart and see what's actually inside. And here's what is inside this GPS discipline oscillator. As you can see, very nice clean design. The front and the back panels are all PCB and everything screws to each other quite nicely. This one is a little bit crooked over here. Some LEDs internally. This one is a power LED. There is a loss of signal LED. You're supposed to see them through the hole or through the little thin section of this front panel. PCB is very difficult to see, but if it's dark enough, it's okay. Now you have 3 main components here. You have the GPS, of course, which is connected to the antenna, and you get the reference from that. There is the STM32 microprocessor, which controls all the communication, interface, and programming and configuring the output synthesizer. The synthesizer is Silicon Labs, and it is a jitter reduction frequency multiplier synthesizer circuit which has 2 outputs. So you can program these 2 outputs to any independent frequency you want, pretty much anywhere from DC to over a gigahertz. And one of them is taken out single-handedly and the other one is taken out differentially. So you can get 2 completely separate frequencies, everything locked to the GPS. It makes it really flexible. And we'll take a look at the schematic and exactly how that is done in just a second. There's also a USB which you can download information into and change the settings of the synthesizer, but there's an EEPROM. So once you download the settings, you power it on, everything is handled automatically. You don't have to have it connected to anything other than power antenna, and it will give you the frequencies you want. It's very nice. We'll go ahead and take a look at the schematic in just a second. Let me just quickly show you what's inside the low pass filter or the band pass filter as well. And here is the 10 megahertz bandpass filter used to create a nice 10 megahertz sinusoid in case you're locking the frequency to 10 megahertz. And this is a tunable LC filter most likely, and it has these L's at the top which you can adjust. Of course, they're already been adjusted for a 10 megahertz bandpass response. One thing I forgot to mention is that everything here is designed and made in Greece, which is great. I don't know how many Greek followers I have, but I have been to Greece and it's a really beautiful place. So if you're from Greece, drop me a line there. All right, now that we know how this is kind of looks like, let's go to the schematic and block diagram, understand how it works, and do some testing. So let's take a look at the schematic of this GPS disciplined oscillator and figure out exactly how it works. Now, as with any GPS unit, you're going to obviously need a GPS module, which is right over here. Now, GPS modules are going to give you some time pulse at the output, and it could be at several different frequencies, 10 megahertz or 1 megahertz, depending on the GPS module. But you don't want to use that and multiply that, because its jitter is not going to be very good. Its phase noise won't be good, but its frequency accuracy is very good. So you could use that potentially. And this configuration, this is exactly what they've done. They're filtering it a little bit with some LC filter and feeding it into one of the clock inputs of the Silicon Labs clock multiplier synthesizer. And that allows them then to combine that with an onboard 50 megahertz 2 part per million temperature compensated crystal oscillator in order to create a very good frequency synthesis unit, which uses the GPS as a reference, but it uses the 50 megahertz crystal as the main crystal of the unit itself. Now, the Silicon Labs clock multiplier jitter reduction unit, which I'm going to talk about in just a second, has two outputs. The version they're using here, the Silicon Labs 5342. You can see that they have taken one of the outputs and they've connected to an SMA, single-ended, and they've taken the other two outputs, the other output differentially, and giving you both the positive and the negative. There are room for the board to even take advantage of the negative output as well from channel 0 if you really want to. But this gives you a really sophisticated and flexible design, because you can set these to be any frequency you want, anywhere from DC pretty much to 1 gigahertz, over a gigahertz, so that you have the flexibility to configure this to run different kinds of frequencies and different kind of synchronization. Now, normally a good one would be to set, let's say, this one to 10 meg, so you can synchronize your 10 megahertz references among many instruments, and then set the differential output to be any other frequency. And not every instrument needs 10 meg as a reference. Sometimes they need 100, sometimes they need 600, depending on what it is that you're using and depending on how high the frequency of operation of the instrument you actually want to synchronize is. So this makes it very powerful. Now, to program this and put them into the EEPROM is a little bit tricky, simply because you have to open the unit and remove a jumper. But there is a Python interface software they have written which talks to the where it is here, talks to the ST microcontroller over there, this ARM processor, so you communicate with that, and then you can program and download and update and then write it to an EEPROM, so that when you power the unit back on, it goes to the last settings you programmed it into. You can also download and use the Silicon Labs clock builder to configure the Silicon Labs IC to any combination you want, and then download those settings using the Python code written by the creators of this module in order to upgrade and configure it. So it is pretty straightforward once you start doing it once and use it and remove the jumpers and figure out how to do this. Unfortunately, you can't do it without opening the unit. At least I don't think you can. But once you figure it out, it works quite nicely. Now, this Silicon Labs clock multiplier jitter device, jitter reduction device, this is this block diagram. You can see it has multiple inputs depending on, I think, which version you're using, but they're using the Silicon Labs 5342, which has two outputs, which both of them, of course, are available. And then here's the clock coming from the GPS. Here's the crystal that is directly on the board, and then you can configure this synthesizer in any way you want to get any frequency you want. So a nice, straightforward architecture, at least from the top view. There's a lot of details in there, obviously, but the combination of EEPROM, USB interface, configurability, frequency choice, and everything that comes together in such a small package, it makes it a very attractive unit to use, especially if you're doing ham radio, or if you just want to synchronize devices in the lab and have a programmable low jitter frequency generator that's locked to the GPS. And here are two outputs. You can see right now they're nicely locked to each other. Occasionally there will be a small movement. Like I said, I don't know how many satellites I have. Normally you do want to have quite a few satellites, and you have to wait for this to settle. But it's very nice and very stable. So as you can see, the 10 megahertz rubidium standard is a square wave because it doesn't have a bandpass filter on it. But look how nice the sinusoid is coming out of this unit. Very well locked and very well filtered to get a nice single tone at the output. Now, this is very sensitive to vibration. Every time there's vibration or movement or even gravity shift on the crystal inside the GPS control oscillator, it will have to readjust and correct that. You can see there's some small movement here. Then again, it's going to go back slowly. So if I were to go ahead and disconnect the GPS antenna, it's going to go into a new mode called the holdover mode. So I'm going to remove the GPS antenna, and when I remove it, we're going to have an unlock condition. Now, as soon as it enters the unlock condition, it's going to do its best to figure out the measurements it had done in the past within a certain window and average those out and apply those in order to keep the correction as closely as possible. Now, of course, once it's not locked, you can see that it's going to be some drift. There's going to be some difference in the frequency. It won't be perfect. But the holdover mode, which is fully configurable, by the way, from the GUI, is very helpful to help maintain the frequency as close as possible using previous measurements in the presence of an unlock condition. Now, I haven't let it build a history. I just had it turned on for only a couple of minutes. So when I let it go, it's going to shift around quite a bit. But if you let it run for a very long time, it gets better and better at preserving the holdover mode. Let's hook it up to the frequency counter and see what that says. Oh, actually forgot to show you the other two outputs. Let's go ahead and enable those and turn the channel 1 and 2 off and turn the other two channel on. And there it is. It's being jittery because we're triggering on a different frequency reference there. Let me go ahead and change the trigger here. I'm going to put the trigger on channel 4. And there it is. There is our signal. This is 200 megahertz, nice and perfectly differential. This is fully configurable to any frequency I want. So I can set it to 1 gigahertz, for example. Maybe we will do that and we'll take a look at the output and the spectrum analyzer as well. But as you can see, it's very powerful to be able to create any frequency that you want. And here's the measured frequency directly on the Fluke PM6685, which is a rubidium standard frequency counter as well. So right now you can see that the last digit is fluctuating occasionally. This is on a 5-second gate. So if you wait a little bit, you'll see that it's going to change back to about 10 megahertz. So it drifts a little bit back and forth for the last significant digit. There it is, that's 10 megahertz again. So yeah, it seems to be working quite nicely. Like I said, I am in the basement. I don't have a lot of the satellites, but nonetheless, it seems to be doing quite well. So it is locked to the satellite. Now, the only other thing I want to measure is to take a look at the 1 gigahertz output. I actually changed the configuration to 1 gig. I want to put it on the spectrum analyzer and see how that waveform looks like and how the phase noise actually looks like at 1 gigahertz. So here's the output of the unit at 1 gigahertz. As you can see, I'm looking at a 1 gigahertz centered tone, and the total sweep is about 50 megahertz here. So we have a couple of tones close by, which I haven't tried to get rid of. This might be possible to eliminate by playing with the PLL settings, as fractional, integer mode, or all the other combinations of bandwidth that you can set. So I haven't tried to get rid of them, but indeed they're going to show up in the phasers. In this case, they're only minus 45 dBc. So if I go to the phase noise itself, you can see the phase noise plot. I'm going from 100 hertz offset to 100 megahertz offset, and the phase noise is characteristic shape you would expect from the instrument's own phase noise combined with the phase noise of the GPS unit itself. This tone is the offset tone that you were seeing on the spectrum, and of course it's going to show up on the phase noise as a tone, but it's ignored mostly because it's averaged out. So if I look at the marker at a 10 kilohertz offset, minus 109 dBc per hertz, it's close to the instrument's phase noise. It's about minus 112. But if you go further, let's say 1 megahertz, we are getting a minus 122 dBc per hertz, which is significantly worse than the instrument. So we're really measuring the GPS unit, which is not bad really for something that's so flexible and can be adjusted. If you really want to see an absolutely good reference phase noise for testing instruments, of course I reviewed and showed you this the Signal Hound unit here, PNCS-1 1 gigahertz phase noise standard, which is so low phase noise that when you connect it to pretty much any of the instruments, it's going to be dominated by the instrument itself. So you're measuring the instrument's phase noise, and that's why they created this. But of course, this is a fixed frequency one, very different from something that you can adjust on the fly by playing around with the register settings. So I think it looks pretty good. Again, all the information from this unit is going to be available underneath the video. If you'd like to purchase one for yourself, I think it's a nice unit if you want to have a very small portable GPS reference that you can configure on the fly. And the last item I want to talk to you about is the TS80 USB soldering iron. Now this is a very popular unit. This is following the TS100, which was also hugely popular. These are USB soldering irons, and they're surprisingly good. You wouldn't think that a USB soldering iron would be so capable, but this is a very refined product at this point. Now this does support quick charge, which means you can put quite a lot of power into it. Now the main advantage of something like this is its portability. For me, it's not going to compete with my JBC station, which costs much more than this. And if I'm going to be at my desk, I'm just going to be using the JBC tools. But if you're going to be portable, especially if you want to power this from a battery pack, it is hugely advantageous. Currently what I have to do is use the portable soldering irons that you have to put fuel in, and of course those are not temperature controlled. This is fully temperature controlled. As an LCD screen, you can set many of the parameters. So let me take a close look at it, and it does support quick charge, but it doesn't support PD, power delivery, which is unfortunate because all of my power banks have that feature. So let's go ahead and see if we can trick it to do that using something in between the battery and the soldering station, and let's take a close look at it. Now in terms of design, this is really well done. All aluminum chassis, everything is precision machined, OLED screen in the front, and the two buttons. Now these two buttons are used to set various parameters, temperature and then settings, but unfortunately in the middle there is no button. I wish there was a button in the middle which would be the select or the enter equivalent of an enter key, because having to press these and long pause them and back and forth and wait for them, it's just, I don't understand why they didn't choose to put one more button in the middle. But you know, it's manageable once you get used to it. Now this is going to be a USB-C connector, 9 volts 2 amps, so about 18 watts can be put into this. The tips are very easily replaceable, and I have to say the quality is really good, and I only have one of them now, but I'm sure they come in multiple ones. Now the heater is of course in the element itself, allowing you to dump the 18 watt of power very close to the device you're trying to solder. So I have to say, very impressed with this. This part unscrews so that you can change the tip while it is hot. Other than that, looks really good. I have to say, very impressed with the design of it. And there is a ground connector at the back which you can connect to this, and then you will have a grounded part as well. It would be probably better if you didn't need to unscrew this to ground this, so you can do it on the go easily. But it does come with its own Allen key to do that. It also does come with its own power supply, which is quick charge capable. So other than that, very nice. Now this is very, very nice cable. I wish all of USB cables were like this. Very flexible. It doesn't burn. It cannot be burnt by the soldering iron itself. Excellent choice for this. So let's go ahead and give it a try. Now I want to run it from my power bank. So let me hook it up to the power bank and see how I can trick it to use PD. So this is the power bank that I want to use this soldering iron with. This is a huge capacity unit. This is a power delivery plus 26,800 milliamp hours, and this is almost the maximum you can actually take with you on the airplane. I've been very happy with it. The only issue is that this works only with power delivery, so it does not trigger the quick charge of this particular soldering iron. So if I connect to it, I'm only going to get 5 volts, in which case this guy will not run at all. But I have one of these guys. This is the AVHZY. I don't know if that's how you pronounce it, but this one is, I purchased this one directly from Amazon, and this one has power delivery capability, so it can test PD of any power source, which means that if I connect my battery bank through this unit, I can trigger the power bank to generate any voltage I want on the PD curve. And then if I connect my soldering iron to this, it will just see that voltage. So I can just directly do it using that technique, which is a little trick that I figured out I could do with this combination of this power bank and a cable. So let's hook it up. I can go ahead and connect this over here, and I can connect this directly into the USB-C input of this guy. And as soon as I do that, it's going to ask me if I'm sure that I understand the power delivery capabilities of it, and I can say I got it, and there it is, nice, generating 5 volts, and it's of course not drawing any current, but I can increase that to 9 volts, I can do 12 volts, 14 volts, and 20 volts. So I can trigger the PD of this using this as an intermediary unit. Now you don't want to go to 20 volts anyway because it's not rated for that, but it doesn't matter. It already knows if the voltage is too high and it will disable everything, which is a fantastic feature, especially if you're doing something like this so you don't damage everything. So now that we have this, we can go ahead and plug the directly to here. Right now we're setting at 12 volts, which is actually just a little bit over the rating of the soldering iron itself, but there will be some IR drop in all the cable because I'm going through so many things. So it doesn't really hurt us from that point of view. We plug this in, and we're going to get powered on. And now I can change and I can turn it on directly. So right now if you look at this number over here, we have about 14 milliamp or so. But as soon as I turn this on, so that I can start heating, there it is. And look at that, it is drawing 2.3 amps at almost 12 volts, which means that it is doing something close to 28 watts, which is crazy. So you're getting 28 watts into a handheld soldering iron. So with 28 watts, and as you can see, it's reaching up to 670 degrees Fahrenheit, which I've set it to, we should be able to do some soldering tests with this. I really like this combination, and it's sitting on my desk, and I can measure the voltage like this, and I can figure out exactly how much current is drawing, and it seems to work. Now, if I go ahead and try and increase the voltage too much, If I go higher, you can see now it says high voltage, so it protects the device against that. If I go back down, it will just simply resume. And if I go way too low, then it will say low voltage. So this firmware that detects this is very handy, and I can then change how much power I want to dump into it. So up to 12 volt it works. Now remember, it actually tells me how much voltage it's getting when the power draw is happening. So when it's doing full power draw, it goes down to 10.35 volts. There's a lot of IR drop, so it would be nice to get a shorter cable directly from, at least from the power bank into this. But other than that, I think it works very well. Let's try some soldering stuff. So let's try soldering something that is on a very large ground plane like this one. This is a fairly big ground plane, of course. It's going to have a lot of thermal mass, and I'm going to try and solder this directly onto it. It's just a test, of course. Now this is not necessarily representative of every ground plane because this doesn't have vias going through it, but nonetheless I think this will be a good test to try. Let's see what we can do. Okay, here we go. This test is being done at 670 degrees Fahrenheit. So let's see what we can do. And I'm going to add some solder and see what it can do for us. Oh yeah, the ground plane, no problem. Look at that. That is great. I mean, we are dumping almost 28 watts into it. But I have to say, I'm really surprised of how well something like this actually works, that I can spread the solder around so easily at 670 degrees Fahrenheit. I mean, look at that. This is great. I would have never thought that a USB soldering iron can work so well. This component is really, really old, so I can't even get the solder to attach to it. There you go. I just got one part of it to start attaching, and then no problem. Once you do that, it flows without any issues. Yeah, look at that. I mean, this whole part is completely molten, and it moves around freely without any issues. Yeah, this is great. So you can see that by having the PD capability and dropping 28 watts or so onto it, it works really well. And I would imagine that for 80% of the things you want to do, it would be no problem. I mean, look at that. It's crazy. I can just paint with solder directly on this ground plane, which is fantastic. Yeah, I'd have to say it works really, really well. And there you have it. I hope you enjoyed the review of these 3 different items. Don't forget to enter a comment and subscribe, because that's how you'll be eligible to win the scope that I showed you at the beginning of the video. And there's going to be a lot more items in the future. And to my Patreon supporters, thank you so much. You guys are incredible. And I'm going to put to good use everything that you're giving to the channel. So I'll see you in the comment section.